Hi everyone, welcome to Snetly. In today's video, we are going to discuss about open loop speed control of 3-phase induction motor with a V by F control technique with a Snetly module level design, as well as we are going to see the real time working of the open loop speed control of induction motor. This is the front view of our Snetly, where we will connect our digital IOs and analog signals. Here we are going to use 3-phase induction motor 0.5 HP rating. And our power module is 3-phase voltage source inverter module, and for the power module we are going to give input source from the auto transformer. These are the hardware component which we are going to use in this application. Induction motor 0.5 HP rating, 3-phase, and the induction motor has been coupled to the encoder for the speed measurement. The encoder pin has been connected to the DB9 connector. Here we are getting totally 5 pins plus 5 volt, and the ground, 2 signals and 1 shield cable. From the encoder we will get the digital input, and we are going to configure it to the Snetly hardware section, where we will connect our digital input pins, which has been shown in the pin configuration. At this particular hardware pin we will get the digital feedback from the encoder, which will be shown in the model level design later. Then we will connect our motor terminal RYB in series with the current sensor for the measurement of 3-phase current waveform. This is the analog signal input area, where we will connect our current sensor, voltage sensor feedback of particular application which we are going to use. Here we will measure the 3-phase induction motor current waveform. The output of current sensor will be connected to the series power module. Connect your RYB phases respectively. Here you can configure any power module has been designed by yourself or some other vendors. And for the power module we are going to give the input from auto transformer output. The maximum DC link for this power module is 300 volt DC. And finally we need to connect our digital output from this Snetly to power module in order to turn on the power semiconductor switches. Totally we having 6 power semiconductor switches in the power module, so we need to require 6 digital output from the Snetly module. From DB25 connector, where we will get the digital output, just connect as per the configuration. And connect to the input of our power module. The level of digital output will be 5 volt level. Internal of the power module we will have a 5 to 15 volt level converter. Even we have direct 15 volt digital output in this Snetly module. If your gate drive is accessing 15 volt level, we can access the pin configuration in Snetly module. this is the total connection which we are required to make in the hardware section. We need to connect to a digital input from the encoder and then digital output to the power module. If you want to measure your current as well as voltage signal, we have to connect to the analog input pin configuration, and then we will go for the module level design for the open loop speed control of induction motor drive with the V/F control technique. Firstly, we will go with the digital input which we are getting from the encoder signal. Let me view the signal how it is coming from the encoder. From the library window, we are going to take the digital input pin which I have assigned in the hardware unit. This is the pin configuration where we connect our encoder output to the input of our Snetly. So totally we are given 4 signal, 5 volt and ground, and 2 signal from the encoder. Here we are connected to the first and third of our input pin configuration. And I am going to take on glitch filter in order to filter the digital input from encoder. The first and third pin will give the signal of A and B from encoder, and for configuration window of glitch filter I am going to give the sample factor of 15. Here you can assign your sample factor from minimum 1 to 10,000 as per your signal configuration values. After clicking on apply register, back to schematic in order to save the configuration value, and to view the signal of your encoder I am going to take on logic analyzer which has been provided in the library window. Click on logic analyzer, connect the output of glitch filter to logic analyzer. There is a simple connection. We will connect our digital input from the encoder to Snetly, and we are going to view it as a, in terms of digital we are getting the output, so we are connecting to the digital input. By manually rotating the motor, we are getting 2 signal from the encoder A and B with a phase shift of 90 degree. This is the data we are getting from the encoder. And nextly we are going to measure the speed of motor. I am going to take a pulse to speed block from the library window. Just right click for configuration of the window. Pulse per revolution, as per the motor data sheet, here we are getting 625 ppr, so I am going to assign the 625 value and then apply register value, back to schematic. You can measure any one of your signal for the speed measurement. Here I am using B signal for the speed measurement. And I am going to take on mean average filter in order to get the average value. So here you need to configure the values in terms of frequency. I am assuming 1000 Hertz. In terms of time, if 10 millisecond, it will average for each 10 millisecond and will give the display value. By clicking on run button or with the live data, manually you can rotate and you can cross check your RPM of the motor with the display feature is been provided in the Snetly. This is simple block development for the speed measurement as well as encoder data viewing in the Snetly tool. Firstly we completed our speed measurement block, then we'll have to go for the Sine PWM generation. To generate a Sine PWM, we require 3 reference signal and 1 carrier signal. Firstly we will develop 3 reference signal. I am going to take one processor. In this processor we can give maximum 8 input and we can get at 8 output. Inside the processor we have separate library window where you can develop module level design internally of the processor. Either with the module level design we can develop, or through the scripting programming, or with the help of assembly code you can develop the logic internally of the processor. Since we require 3 sine, I am taking 3 sine block from the library window, and the 3 sine have a phase shift of plus 120 degree and minus 120 degree. I am going to assign the values in terms of radian, and here I am going to take a weight sample in terms of completion of one cycle. Here I am assuming the sample frequency of 50 kilohertz, so our time period will be 20 microsecond. For each 20 microsecond our data will be retrieving from the processor. From the library of processor we can develop each and every blocks internally would be provided, so we need to configure as per our application development. In previous video we already developed for the PMSM control. With the rotor feedback we have generated 3 reference signal. Here we are generating manual sine with a phase shift of plus 120 and minus 120. Here input pin will be in terms of D0 to D7, and our output will be Q0 to Q7. So totally maximum 8 input you can give from the external of processor, and you can get 8 output from the internal of processor. Here we have taken m into sin x. M is nothing but the amplitude we are going to multiply with this sine value. Since we are going for a variable voltage and variable frequency, I am going for a external control of my amplitude and frequency. Here D0 will be our frequency and D1 will be our amplitude control, which we need to give from the external point to the processor input. Q0 will be our R phase output, and Q1 will be our Y phase output, and Q2 will be our B phase output. After developing the block, build all and back to schematic. Now we have developed a model level design inside the scientific processor type 1. Now we need to give the input to the processor. So I am taking a constant block and one more knob for a variable control. In constant I am assuming the value 0.97 for the amplitude of sine. The second input will be 50 Hz sine frequency value. Inside the knob I am going to configure the value of 0.1 to maximum 1. Whenever you are configuring the value, try to make apply register in order to save the data inside the configuration window. From the library window I am going to take a math block. Just right click for the configuration window. Here we have two channels, channel 0 and channel 1. By simply giving the configuration value, our block will be perform the addition, multiplication, subtraction like that. Here I am giving the configuration value as 33, so the block will be perform the multiplication factor. Here I am giving A0 to the knob as well as 0.97 to B0. These two will be multiply and will give the output to Q0, so we will get the amplitude value of sine. Similarly for frequency, I am going to connect to the A1 and B1. Knob value will be multiplied with the constant and we will get the output from the math model. From the math model we will give the input to the processor. From the processor we will get the 3-phase sine RYB with a phase shift of 120 degree, which will be shown in the display. I click on run button. You can observe here 3-phase reference signal with the help of internal DSO. The DSO you can configure your amplitude value as well as time value. Here you can see your 3-phase sine waveform with a phase shift of 120 degree. By simply varying the value of knob, our amplitude as well as frequency value will be changing, which is nothing but the V by F amplitude as well as frequency has been varying at a simultaneously. Now we need to compare the reference signal with a carrier signal. Before that I will take a carrier as a triangle signal. So I need to configure the triangle block. So I am keeping minimum and maximum value -1 to +1 and the frequency of 4 kHz. And let me take one comparator block. Now we need to compare the reference signal with a carrier signal and we will get the 6 digital output from the comparator output. Simply connect triangle output to the carrier and Q0 to first input and Q1 to second input and Q3 to third input. Nothing but the reference signal of RYB. And then let me take a dead time controller. In dead time controller we can configure the value from minimum 1 microsecond to 100 microsecond, 1000 microsecond. To view the output I am going to take a logic analyzer, just connecting the output of dead time to the logic analyzer. By simply varying the knob, now our duty cycle will be changing in the logic analyzer. Firstly we have developed the speed measurement block and then we have developed our Sine PWM blocks. Now we are getting the digital output we need to connect these digital output to the external hardware unit of 3-phase voltage source power module. So we need to configure the pins which I have shown in the previous video. To DB25 connector we need to connect the digital output. In the help window we can see the pin configuration provided. So we are generating totally 6 digital output in this block. To run a 3-phase induction motor control we require only 6 digital output. So we are generating 6 digital output. And one more thing, we want to measure our 3-phase current measurement. So we need to connect the analog input to the block. Let me take from the library window analog input and take an internal DSO. By right clicking on the help window you can see the pin configuration where we need to connect our motor terminals ROIB. Here the configuration values has been given in the left side and the external pin connections will be provided on the right side of you. Here we are going to measure only current measurement. The maximum measurement value will be plus or minus 20 amps. And you can adjust your offset as well as gain as per our signal we are getting from the hardware section. Here I am going with the default value of typically gain and as well as offset value has been provided in the help window. First 3 channel has been connected to the current sensor signal. So I am assuming the gain value 0.01221 default value I am assuming. Based on our signal we can adjust our amplitude, simply gain value as well as offset value you can adjust. I am connecting the output of analog to the DSO. This is the complete module level design for a open loop speed control of induction motor with VBF technique. First we have developed the speed measurement block with the help of encoder we are getting from the motor drive. Run the MCB and apply your maximum VDC link, and you can observe here motor has been running. Once the motor starts running, our current waveform has been shown in the analog inputs. Here you can observe here 3-phase current waveform of ROIB has been shown in the DSO. This is the internal DSO. Inside of report disk we can give a DSO signal as well as plotter signal. In order to take the waveform capturing, you can either through mail you can send it or screenshot you can take it. just simply connect whichever signal you are connected to the DSO, like number 1 to 12 channel we have been having internally, so we can take at a time 12 channel waveform outputs. Here I am just connecting the current sensor output to the report disk to measure the current waveforms. In model level design, I have split it into 3 sections for clear understanding. Firstly, we have designed the digital input where we will get from the encoder, and we have observed the waveform. From the encoder signal, we are used for the speed measurement block. So we are internally having a block pulse to speed measurement, and then we are going to the current measurement, and third will be our Sine PWM generation. Here in report disk, you can observe your current waveform. The speed measurement has been shown in the display. By simply varying the knob value, we can observe the speed value has been increasing as well as decreasing based on the modulation index we are getting. By increasing our knob value, our amplitude of sine as well as frequency will be changing. Based on the changes, we will get the changes in modulation index. So once the modulation index changes, duty cycle of our power semiconductors will be increasing. So based on that, we will get a respective output voltage in the power model. So the motor speed varies. On motor live running, you can clearly observe the encoder signal as well as speed measurement and your PWM generation and the current waveform generation of motor. Here we are going for the maximum VDC of 300 volt, and we can observe here rated RPM in the display point. While the system is running, it is easily we can configure the value without shutting off your hardware section. I am simply changing the frequency of triangle so that the switching frequency of power semiconductor switches will be changes, which will nothing affect our Snetly power module as well as your hardware section. You can linearly changes the value of each and every blocks without turning off your hardware components. In Snetly, we are developing the model level design inside the controller. Whatever we are doing the code level code composing logics, each and everything here we are developing in the model level design. In next video we will see about the closed loop speed control of 3-phase induction motor with a PI control algorithm.